Hello, everyone. So in the last section, we defined limits, and we did a couple of simple examples involving limits. And basically, we had two different methods for calculating limits. So right now, we don't have too many tools. But last time, the methods we looked at were using calculators. And we said that works sometimes for simple examples, but also there are some problems. For instance, rounding errors, or maybe a couple of values are not really representative of what's going on. And the other method we had was graphing, but graphing doesn't always work and it's not always easy to graph a function. So really we need some more systematic tools in order to do that. And since we're mathematicians, we want to be as efficient as possible and we want to have a few tools that we can use for as many examples as possible. And that's where we're going with limit laws. So we want to be able to start with a couple of limits and then build them up using these so-called limit laws to handle lots and lots of different cases. So let's look at what these laws involve. So basically the idea is we start with a couple of limits and we want to build them up to work in lots of different cases. So suppose we already know two limits, say the limit of f as x tends to a and the limit of g as x tends to a, and we have some constant c. And then let's see how to build those up to calculate more limits. So these are going to be the rules, and then we're going to see some examples using these rules. So the first rule is that the limit of f of x plus g of x as x tends to a is the limit of f of x plus the limit of g of x if the limit of f and the limit of g both exist. So in other words, we can interchange sums and limits provided the individual limits exist. Okay. So why does this make sense? I don't want to prove it in details to you too carefully because we don't need to do that, but just as an idea, suppose that f of x tends to c, some number c, let's say. So f of x is getting very close to c. And suppose that g of x tends to some other number, let's say d. So g of x is getting very close to d. Well, if f of x is getting close to c and g of x is getting close to d as x gets close to a, then f of x plus g of x is getting close to c plus d. Okay? Or in other words, the limit of f plus g is the limit of f plus the limit of g. Okay? And similarly, the limit of f minus g is the limit of f minus the limit of g if both of the individual limits exist. The limit of a constant times f is a constant times the limit of f. For instance, if f of x was getting close to 10, or if the limit of f of x was 10, so that means f of x is getting close to 10, then the limit of twice f of x is 2 times 10 will be 20, right? Because 2 times f of x would be getting close to 2 times 10 and would be getting close to 20. The limit of a product, so the limit of f of x times g of x is the product of the limits, so the limit of f of x times the limit of g of x. And similarly with quotient, so the limit of f divided by g is the limit of f divided by the limit of g, except here we have to be really careful that nothing on the bottom is allowed to be 0. So we have to insist that the limit of g of x as x tends to a is not equal to 0. Okay, and here I wrote everything for two-sided limits, but we also have similar rules if we replace all of the two-sided limits by one-sided limits, so x tends to a plus and x tends to a minus. Okay, so let's see a couple of simple examples where we use these rules. So here, let's say there are two functions. So f of x is 1 minus x if x is less than 0, 1 plus x if x is bigger or equal to 0. So I made the graph, so it's linear to the left of 0, linear to the right of 0. It looks something like this. It intersects at 1. And g of x is 5e to the x. So I drew the graph of g. And we can see that as x tends to 0, both of the limits of f and the limit of g exist, right? F of x tends to 1 and g of x tends to 5. There's nothing strange going on. They're pretty smooth, pretty regular functions. Limit of f is 1, the limit of g is 5 as x tends to 0. And let's look at some functions that are not f and g, but are related to those. So if, for instance, we look at f of x plus 3g of x, then we don't have to plug things in a calculator. We don't have to graph f plus 3g of x. If we want to find the limit of f of x plus 3g of x, then provided we know that the limit of f and the limit of g both exist, which we do, then we can say the limit of the sum is the sum of the limits. So the limit of f plus 3g is the limit of f plus 3 times the limit of plus the limit of 3g. And the limit of 3g is 3 times the limit of g. Okay, so we can kind of break it apart. And then we can look at the limit of f and the limit of g separately. Okay, we said the limit of f is 1, the limit of g is 5. So we're going to get 1 plus 3 times 5, we get 16. Okay. And similarly with products, right, we know that the limit of f as x tends to 0 exists, the limit of g as x tends to 0 exists. So the limit laws tell us that we can calculate the limit of f times g. It's going to be the limit of f times the limit of g. So in this case, we're going to get 1 times 5, we're going to get 5. Okay. And then finally, we have quite a complicated expression here, f plus 3g divided by g minus f. So there are going to be a couple of steps. So firstly, it's a quotient. So we're going to say the limit of the quotient is the limit of the numerator divided by the numerator of the denominator. provided the limit of the denominator is not 0, which we have to check in a second. Okay, and then the limit of the numerator we can separate as the limit of f plus 3 times the limit of g, as we did just a second ago. And then the limit of the denominator we can split as the limit of g minus the limit of f. Okay, and then if we look at the numerator, okay, we said the limit of f was 1 and the limit of g was 5. So on the top we're going to get 16. And then on the bottom we're going to get 5 minus 1, we're going to get 4. So 16 minus 4 equals hopefully 4. So basically the idea is we start with a couple of limits we know, and then we can break them down using the limit of the sum is the sum of the limits. Similarly with differences, the limit of a constant is the constant times the limit. Limit of a product is the product of the limits. Limit of the quotient is the quotient of the limits, provided the bottom is not 0. So we can calculate limits of complicated expressions using the limits of the simpler individual components by breaking it apart. Okay, so here are a couple more limit laws, and we can do the same thing with powers. So the limit of f of x to the power n is the limit of f of x all to the power n, provided n is a positive integer. We're going to say something else with roots in a second. The limit of a constant is just a constant. So this sounds kind of trivial, but it occasionally comes in handy. So why does that make sense? Okay, if x is tending to some number, here I guess the c's could be different. So whatever x is approaching, a constant will remain a constant. So the only thing a constant can approach is a constant. So wherever you take a limit, the constant just goes to the constant itself. Okay. The limit as x tends to a of x is just a, right? As x gets very close to some number, whatever that number is, x is just going to get close to the same number, right? X is the identity. If x tends to 2, then x is tending to 2. Okay, we can do the same thing with roots. So we can interchange roots and limits. The limit of a root of f of x is the root of the limit of f of x. So we can bring the limit inside the root. But here we have to insist that everything is supposed to make sense. So for instance, if n is even, for instance, if n was 2, that would mean we're taking a square root. And we can't take square roots of negative numbers. So if we're taking an even root, then we have to insist that the thing inside is supposed to be positive. So here, if n was even, we have to insist the limit of f is positive. Otherwise, we would have square roots of negative numbers, which is terrible. Okay, and there are a couple of consequences if we combine these rules together. So for instance, if we combine 3 and the power rule, we get that the limit as x tends to a of x to the n is a to the n. So this is useful, for instance, with polynomials that have things like x cubed, x squared, and so on, as we'll see in a second. Okay, the limit of a root, the nth root of x, tends to the nth root of a. Provided, I should say here, that a is strictly bigger than 0, right? We don't want to take square roots of negative numbers. So I guess the moral here is that we can calculate limits involving sums and products and differences and quotients and powers by breaking it apart and looking at the limits of the individual pieces instead. And usually the individual pieces are simpler than looking at the whole expression by itself. So if you're faced with a complicated looking limit, see if you can break it down into the individual components. So let's look at a couple examples. Suppose we're looking at the limit as x tends to minus 1 of x squared plus 5x plus 3. Okay, so it's some polynomial. And a similar argument is going to work with any polynomial. Then first we notice it's a sum of some things. So let's split it into a sum of limits. So the limit of the sum is the sum of the limits, provided, which we have to check that the limit of each individual component exists. Okay, and then so we can look at separately at the limit as x tends to minus 1 of x squared and the limit of 5x and the limit of 3. And instead of thinking about everything all at once, we can just think of each of those separately. So for example, first we have to look at the limit of x squared. Well, we said just before that we can interchange the limits and powers here, right? The limit is x tends to a of x to the n equals a to the n. So in particular, the limit of x squared is going to be a squared. Okay, but here we are looking at the limit as x tends to minus 1. So that's going to be minus 1 squared. That's going to become plus 1. Okay, and then secondly, we interchange the limit and the constant. So we bring out the 5. The limit of 5x is 5 times the limit of x. That's going to be 5 times minus 1. And then here we have a constant, and wherever we take the limit of a constant, the constant just stays constant, right? Whatever x approaches, it doesn't matter what's happening with x, the 3 is just the 3. So that's going to stay constant. So we worked out the limits of each individual piece separately, and now, okay, we just have some numbers, we add them up, so we get 1 minus 5 plus 3, which is minus 1. Okay. So let's see some more examples. So another one with polynomials. So x to the 4 minus 3x. So it's a limit of a difference. So we can interchange instead of looking at the limit of the difference, we can look at the difference of the limits. So we can look at the limit of x to the 4 minus the limit of 3 times x. So we work on each of those separately. If we look at the limit as x tends to minus 1 as x to the 4, okay, we said the limit of x to the n is a to the n. Here we're saying x goes to minus 1, so that's going to be minus 1 to the 4. We just bring the limit inside the power. And the same with constants again, right? The limit of a constant times a function is just a constant times the limit. So we bring the constant out, 3 times the limit of x. That's going to be 3 times minus 1. Okay, and then we add this up. We get 1 minus 3, which does not seem to be 4. So I should check that. It should be minus 2. Sorry about that. Sorry, it should be 1 minus minus 3, right? Here is a minus. Here I pick up another minus. It should be 1 minus minus 3. So here is a minus. 1 minus minus 3 equals 4. Okay. So rather than me axing this whole thing and re-recording, let me just say that here is a lesson. Be very careful with the minus minus, right? So here is a minus 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 3. 1 minus minus 3 gives me 4. Please be very careful with your minus signs. However old you are, it will still come and get you. Okay, so we said the limit of this one was minus 1, the limit of this one was 4. And these were already pretty complicated looking expressions, but we can even go ahead and combine them, right? So here I want to look at the limit of this huge mess. And rather than expand everything and try to use the rules again, let's just notice that we already calculated the limit of this first term, and we already calculated the limit of this second term, and it's a product. So the limit of a product is the product of the limits. Okay, and then we already calculated the limit of each individual component, right? There was minus 1 for the first one, there was 4 for the second one. Those were example 1 and example 2 we just talked about. So we just multiply them, we get minus 4. Okay, so you see with the limit laws, they look pretty simple, they look pretty obvious. But if we just keep combining them, and we can combine them more than once, right? We keep combining them as many times as we need to, we can get the limit of way more complicated expressions, okay? And similarly here is an even more complicated expression, which is based on the previous ones, right? Here is the x squared plus 5x plus 3 again. Here is the square root of, again, the x to the 4 minus 3x. So the limit of a quotient is the quotient of the limits, provided we have to check that the limit of the bottom is going to be non-zero, which we have to check in a second. Okay, the limit of the top is what we already calculated. It was minus 1. The limit of the bottom, okay, the limit of a square root is the square root of the limit, provided the inside is going to be bigger than 0. Okay, and we already calculated that the limit of x to the 4 minus 3x is going to be 4. Okay, so the limit of the square root is going to be the square root of the limit. We're going to get the square root of 4. So overall, we get minus 1 over the square root of 4. We get minus 1 over 2. Okay, so just keep applying the limit law, sometimes more than once. If you have roots, if you have quotients, you have to check the bottom is non-zero or the inside of an even root is strictly bigger than 0. But mostly, as long as all the limits exist, you can interchange limits and sums, products, powers, and quotients, and so on. Okay, so maybe one thing we noticed here with the polynomial is that with the polynomials, basically we are just substituting in, right? When we calculated, going back a second, when we calculated the limit of x squared plus 5x plus 3, I mean, we did something fancy. We used the limit laws, but basically we got the same answer as if we plugged in minus 1 into the polynomial and just calculated. And similarly with this polynomial. And this doesn't work with all functions. So substitution doesn't work for every function, but it works for polynomials. Okay, so this is what I want to record here. If we have a polynomial or we have a rational function, so a rational function just means one polynomial divided by another polynomial, and we have a number in the domain, then if we take the limit, that's just the same as plugging in. Okay, so it doesn't work for everything, but for polynomials or quotients of polynomials, a being in the domain means that if we have a rational function, then the bottom is not 0. So for these nice types of functions, we can just plug in to find the limit. So these are very simple functions for finding limits. Again, here I want to emphasize plugging in does not work for every function. For instance, if we look at this function, f of x, which is 0, only at x equals 0, and f of x is 1 for every other x. If we try to take the limit as x goes to 0, remember back in the definition of a limit, we don't care at all about what happens at the limit point. So if we look at what happens as x tends to 0, we're looking at what happens as x gets close to 0, but not at x equals 0. So I completely forget what happens at x equals 0. I only look at what happens for x close to 0, which puts me in the land of f of x equals 1. Okay, all the values are 1. The only thing it can get close to if I disregard the 0 is 1. So for this function, the limit as x goes to 0 will be 1. But if I just plug in, I would get f of 0, which is 0. Okay, so substitution does not work for every function. And okay, the category of functions for which it does work are somehow nice functions for us, right? They're functions for which it's very easy to find limits. We just substitute. They're going to be called continuous functions. Okay, so we'll talk a little bit about this later. But for the moment, what we need to remember is if we have a polynomial or a rational function and we're trying to take the limit to somewhere in the domain, for those functions, you can just substitute, but don't assume you can substitute if you don't have one of these nice functions. Okay, that's everything for today. So remember, the limit laws are a good way to find limits of complicated expressions by breaking them up into simpler pieces where you can hopefully find the limits of the individual pieces. Thanks, everyone. See you next time.